we're going to learn about what goes into learning a model and how to find the right model. So this is basically talking about how fitting happens, and then how do you actually find the right model to fit something. And then later we'll go into much more detail, and you can look this up on the website. So our basic structure of today's talk is going to be learning a model and then finding the right model. And in learning the model itself, there's going to be three parts. There's going to be risk-n models, noiseless learning, and noisy learning. And some of these things may be a little bit broken right now, but we'll fix those. You just need to pay attention to the slides. Risk-n models is what we'll start off with. Okay, how do machines learn? And so this will be a very kind of interactive session. I will keep sort of like stopping myself and asking you questions. When I do that, please, just sound out the question. Just interrupt, unmute yourself, give me the answer, make a comment, whatever, and then go back on mute. So our first thing is, we want to fit a model to data. Here is some data. So we would like to learn what function or model, these are the words we're going to use, generated this data, okay? So what does it mean to say generated this data, right? That's probably the first question you want to ask. It does not mean that the data came directly from the function. It means that somehow or the other, there was some kind of physical process, some social process, some other process that gave rise to this data, but there was also some regular kind of noise in it. Why noise? Noise tends to happen sort of like all over the place, right? I mean, if you're measuring something with a ruler, you're going to have some noise because you didn't sort of like attach the ruler's ends kind of properly. If you're in a credit bureau and you're trying to figure out whether I'm going to default on my loan payment or not, you don't know all the stuff about my life, whether I just got laid off from a job or something of that sort. And so if there are two people, exactly the same salary, one just got laid off and one does not got laid off, then the prediction for one may be default and the prediction for the other may be no default. So all of these things generate noise in our system. Our function to predict this kind of person's credit score may be a perfectly reasonable one. But beyond and above that, what happens kind of depends upon the situation. Okay, so we don't know what this function is. And in fact, think about it, you're not God, so nobody's telling you what this function is. And because nobody's telling you what this function is, so we do not know what this function f is, and the best we can do is to find some other function g that fits this data best. As I said, we're not God, so we don't know what generated the data. So we try things, and hopefully they work, right? Okay, so that's the basic setup of our situation. So to make this a little bit systematic, let's organize our functions, and we'll organize our functions into something called hypothesis spaces. So what's a hypothesis space? Is just a bunch of functions. It's a big fat name for something very simple. It's just a bunch of functions. For example, look at the function I've written on the left over there. It's basically going theta 0 plus theta 1x plus theta 2x squared plus theta 3x cubed and so on and so forth up to some degree of the polynomial d. So this, as you probably know from math class way back in the past at some point, is a polynomial. An example is 4 plus 5x, or 4 plus 5x plus 6x squared, or 4 plus 5x plus 6x squared plus 7x cubed, or something like that. Anything, cook it up, right? So when I go to x cubed, that's an order 3 polynomial. When it's like squared, it's an order 2 polynomial, and so on and so forth. So these are the sort of like different polynomial complexities that kind of come up. Okay. So what we're going to do is we'll organize these hypothesis spaces by the degree of the polynomial. So let's say all the linear functions is one set. All the quadratic functions is another set. All the cubic functions is a third set. All the quartic functions is a fourth set. And we'll call each of these a hypothesis space. Okay, so that's going to be the game we'll play. Now, for example, the hypothesis space H1 is all H1 of x. Anything of the form theta 0 plus theta 1x is the hypothesis space H1. And H20, which is the other hypothesis space we're going to kind of concentrate on today, for reasons that will become clear very soon, is the set of all 20th order polynomials, okay? And this is how you sort of like define these kind of polynomials in Python. Here's a little example, and here's a little plot. Now, I want you to see this plot and tell me if there's something interesting that you notice about the green plot, the green line, or the green curve rather. After all, it is a cubic.
The other two curves seem to touch the green plot.
They do, but what's weird about this green plot?
Very large number of variations.
A very large negative values, right? And so let's ask the question, why do you think there are very large negative values? Look at H3 on the left and tell me why you think there are large negative values.
It has got a x cubed term.
It's got an x cubed term, okay. So that's putting, and at negative values, that's putting a large amount of negative value, agreed, okay. So at minus 10, you are seeing minus 10 to the 3, which is minus 1,000, and multiplied by 5, that's minus 5,000. What else?
Your coefficient of x squared is also negative. So that also
Coefficient of x squared is negative and it's large, right?
Yeah.
Okay, so I think you got it. The point I'm trying to make over here is that if you have large sort of negative terms, things becoming largely negative or large negative coefficients in polynomials, you can get extremely large values both on the positive side and on the negative side. So just keep that in mind. That'll be kind of important as we go forward. Okay, so let's ask a question. What does it mean to fit? So that's that previous data which we saw. And we're asking the question, what does it mean to fit a function to this data? So if you saw this plot over here, how would you think of fitting this data?
Minimize the vertical errors.
Minimize the vertical errors, right? Yeah, absolutely. So you might say minimize the vertical errors, and how might you do that? We just add all the errors up?
At least square.
And why would you square them?
Because otherwise they might get cancelled, the positive and negative errors.
The positive and negative might get cancelled. Good point, right? So we could take the absolute values and add them too, right? If we wanted to fix that problem. Make sense? But as you said, and you came up with a good suggestion. Let's just square them. Let's just take the difference and square it and add it, and this way we won't have this problem. Okay, so there you go. So that's the way you would do this. Okay, so that's, yeah, go ahead.
Yeah, so the previous, in this particular side, RD, whatever has been written, the sum of square errors, is it also the cost function?
This is also called a cost function. The risk function, cost function, it's the same thing. Error. Okay. You'll see these words, absolutely. You'll see these words used interchangeably. And notice that thank you for stopping me there, because one thing I forgot to say, which is notice the notation over here. It's saying R, the risk or the error on this data set D as a function of some hypothesis H, right? So we have some hypothesis H which belongs to the set of all possible straight lines, the capital H1, so to speak. And this is the error associated with it. And so now what's my idea going to be to fit?
Minimize it.
I'm going to minimize it. So kind of the word, visually, what does that mean? I'm going to sort of like put every possible straight line out there, right? Which I can find. Every possible member of the hypothesis set, capital H1. Every possible small h1 function, I'm going to put it there. And I'm going to find that function, that straight line, which minimizes the error. Make sense?
Yeah.
So in other words, this risk or error is actually a function of a function.
Yep.
Yeah. So you're finding the function which minimizes the error. Of course, you do it in a very simple way, right? You say it's intercept plus slope times x, and you'll differentiate with respect to the slope, and you'll differentiate with respect to the intercept, set that to 0, and boom, you got your answer of the slope and intercept. And once you got your answer for the slope and intercept, you combine them together, and you get the best fit line. So does that idea make sense?
Yeah.
Yeah? Okay. So keep that idea in mind. Okay, so that's the idea we're going to go through. Does this need to be a straight line, or can it be anything I want?
Anything.
It can be anything, right? It could be a neural network. It could be a polynomial. It could be just about everything I wanted.
Depending on the data.
Yeah, depending on the data, right? I might choose something else. Okay, so far so good. All right, so let's actually do something fun and funny. This is a sine curve. F of x is a sine curve. Actually, to be very precise, it's sine of pi times x. And I've taken the sine curve and I've added some noise to it. And then I've removed the curve and I've just left the data that came out of it. So this is about, I think I generated 100 points to make this graph for you. Okay. So if there is noise, I will still call f of x is equal to sine of pi times x, my generating function, my generating model. If there's noise, I'll add it in as this term epsilon over here. In the situation where there is no noise, I put epsilon is equal to 0. Then my y is just equal to f of x, and I'll get a curve that looks something like this. And you can see this basically just is exactly on the sine pi times x line. And this one isn't because I've added some noise in. Okay. So fitting a hypothesis to any of these functions is what we want to do. But specifically, I'm going to call fitting a function in the situation in which epsilon is equal to 0. I'm going to call that approximation because that's our usual sense of approximation. There's no statistics here. It's just that you said, hey, I've got some data. It's come from a function. Find me the function. And I'm like, well, I didn't know it came from a sine. I'm going to try all kinds of things to try and fit it. That's the game I'm going to play. So far, so good. Any questions?
Nope.
No? Okay.
I had one question.
Yeah, go ahead.
So while we're calculating the error, all we know is the data points, and so we're subtracting our hypothesis from the data points.
That's right. So we are calculating our hypothesis at the x's of those data points.
Yeah.
As you
so
see,
if we wanted to find the approximation, then how would we know the so the y contains the function value plus some noise. So how would we subtract the noise? How would we know about the noise?
We don't know. We can't subtract the noise out.
Right. Okay.
Yeah, you're out of luck. You can't subtract the noise out. So you'll just be doing y minus h1 of x.
Right.
Squaring it, adding it over all the points you have in your data set, all these 100 points over here. That's what you'll be doing.
Thanks.
Okay.
I have a question as well.
Yes, go ahead.
In the previous slide, the equation, did that represent something similar to a line y equal to mx plus c?
This equation here?
No, the next slide.
Next slide.
Yeah, this one.
No, it's saying that I don't know what f of x is. This is talking about the generating function. See, imagine you a God, okay, for a second. And you said, I'm going to give Rahul some data, which has come from a sine curve, and I'm going to add some random noise into it. That sine curve is this f of x, okay? Then you came to me and you gave me the data, and you said, I'm a sort of like, not so nice God. I'm actually going to give you this, but I'm not going to tell you which curve it came from. You figure it out yourself.
No, my question is, does it depict y equal to mx plus c?
No, that would be a straight line, right?
Yeah. Okay. So here you're trying to say that the f of x, the function, can be any type of line.
Any type of anything. It's some kind of it's a function that was generated somehow. Right? It need not even be a very explicit process, right? It could be some kind of weird physics differential equation solving. It could be, a sine curve like I did over here. It could be data coming from a self-driving car. It could be anything.
Right. Okay. Thank you.
Yeah. So it's what we'll call the target or the generating function. We're trying to figure out what this function was.
Just a doubt, but in that sense, then the noise also may not be additive all the time, right?
Oh, absolutely. Noise may not be additive all the time. So I've taken only one situation here where the noise is additive. You're absolutely right. The noise may not be additive, and it may not even be it may not even have the same characteristics at every point. But if we can't solve the simple problem, we won't be able to make any headway on the more complicated ones, right?
Yeah, cool. Makes sense.
Yeah. So let's just talk about additive noise coming from some simple noise model of some kind or the other. But let's even actually go simpler. Let's start by saying no noise. We just want to fit this. The funny thing about this is that nobody told us that this was a sine curve. And we never went through school, so we never knew this was a sine curve. And so we want to figure out what it is. So what do? We come up with the functions we know, the polynomials, say for example, and try and fit this curve. So that's the game we're going to play. There is a complication though in this game. The complication is that, suppose I didn't give you all 100 of these points. Suppose I only gave you about 30 of them, or 20 of them, or something like that. And why would you think of something like this? Well, think of elections, right? So there are elections coming up in the US very soon. The US has about 300 million people. Is it humanly possible to go ask 300 million people what they are doing? Who they're going to vote for?
Not at all.
Not at all, right? What do you typically do? What does a pollster typically do, right? So they'll go out and ask 1,000 people. And they'll ask those 1,000 people who they vote for, and they'll try and actually get the 1,000 people from all walks of life, right? Men, women, white people, black people, Asians, all kinds of stuff. And they'll try and balance it across these things, at the same level as the population has those different mixtures of groups. And then they'll ask people, and people will tell them. So basically, you're trying to predict there who's going to win the election from a sample. And that's what our life usually is like. We don't get all the data because we don't have infinite resources. We don't get all 100 points. We get 20, 30 points, and we are asked to tell what this function f of x is that generated this data. So is the setup of the problem clear?
Yes, Rahul.
Yeah?
Yeah.
Okay.
Yeah.
Okay, so we don't necessarily even have a population of like 100 points or millions of people. You have a sample of 1,000 people or a sample of 30 points or something. Okay, so let's go. Let's do this. So we're not all the details of the code and the Python and everything I'm not going to talk about today. This is meant to be a more sort of like, you don't need to know Python to follow what I'm talking about right now. But all the details of how these things were fit and everything are there in the notes and the notebooks, which are on the website. So please go take a look at those, and we can go from there. Feel free to ask me questions either on Discourse or on our Slack, and we can have conversations about it. So here is my best fit straight line to this. Okay, how did I do it? I essentially said, okay, this is my data. Let me say h1 of x is theta 0 plus theta 1x, and then let me subtract each one of those, square those, and figure out what theta 0 and theta 1 should be, right? Find the one that has the minimum distance. And this is what it looks like. Do you think this is a good fit?
No, sir.
No, right? It's a kind of bad fit.
No.
Okay. But it's a fit. It does roughly get this kind of idea that the sine curve looks like it's going up, right? Of course, if I do one more cycle of the sine curve, everything will go crazy. It's a little bit of a lie over there. Okay, now, say I have a sample of only 20 points, right? The sample is these orange squares. And I now try and plot. I now try and do a fit. And this fit is now shown to you by this orange line. Now it gets the rough idea right, that the sine curve is kind of increasing. But it does not get the same, it does not occur at the same place, right? As the blue line, which I fit on the entire population. So what would happen if I took a different sample? Would I get the same orange line?
No.
No, we won't.
No, right? Because it depends on how I chose those 20 points from the sample, right?
Yeah.
So what's the advantage of having large samples?
Lesser error or lesser noise, like your answer will be more precise.
The answer will be more precise and closer to the answer you got on the population, right?
Yeah.
So that's kind of intuitive. That makes sort of intuitive sense that that's going to happen. So you will have less error. Exactly. Let me see, do I have the slide here? No, I have that slide in the next one. Okay. So, yeah, so absolutely. So that's the kind of effect you're going to get. You see this approximation is bad and the sample approximation is just as bad. They both get the rough direction right, and that's I guess the best we could expect of this model. Okay, so let's just recap. What have we done so far, right? So far, we've done y is equal to f of x over here. That's some target we have. And from this target, we have some data. Maybe we add noise to it. Maybe we don't add noise to it. We'll come back to this, this noise situation later. Okay. Then you have some input distribution P of x, which is basically saying how are the x distributed across? You can see that, for example, in the sine curve, the blue x's are distributed very uniformly across the entire -1 to 1 range over here, whereas the orange ones are distributed somewhat differently, as you might expect, because it's a sample. Once you get that, you put those things together and you have the x and the y's, and you have a learning algorithm out here, which is linear regression over here, or polynomial regression over here, where you're basically taking this risk, which is the f of x minus what you predict, squaring it, and then minimizing it with respect to the to the parameters of the line, or the parameters of the quadratic function, or the parameters of the cubic function. So that's the basic idea, okay, of this system. Okay, so here's an example. Now I take a third order polynomial, basically a cubic, something of the type a plus bx plus cx squared plus dx cubed. And now I use that, and I use exactly the same idea, right? I use the cubic, I make a prediction, I subtract it from the data given to me on the sine curve, and I find what my fits are. And you can see over here that the population curve is green and the sample curve is red. And they both do a much better job of actually capturing the sineness of the curve. And that kind of makes sense. Can somebody tell me why that makes sense?
There's more room for adjusting parameters when you talk about cubic polynomials.
Exactly, beautiful. That's an absolutely fabulous answer. There is more room for adjusting parameters. And now we're talking about a cubic, so you're talking about 4 parameters. You can combine these together. You know, you have an x cubed term, so it can go negative as much as you want it to, and you can add that thing in, and then you're all good, and you can get a much better fit. So one of the things that you can see is that as you make this a little bit more complex, and if I had actually taken a quartic or a quintic, I could have probably done an even better job. So the more complex I make my models, the better I can do to fit my data. You know. Now, does that make sense to you? Let's take the sample. I have 20 data points. Can I fit a model on this with absolutely 0 error?
We can.
Okay, and can you tell me what kind of a model would that would be?
A perfect fit.
Yes, but so why would a 20 order polynomial give you a perfect fit? Or actually, it would be a 19th order polynomial would give you a perfect fit. You don't even have to go to 20.
Because it doesn't have any noise in that. So maybe we can get.
No, it has nothing to do with noise.
It's easier to fit.
So does it have something to do with the Taylor approximation for?
Nope, nothing to do with the Taylor approximation.
Because it matches the data given to us exactly.
Exactly, it matches the data given to us exactly. I can write 20 simultaneous equations in the coefficients, right? With 20 points. And with 20 simultaneous equations and 20 things to find, I'm done, right?
Right.
And so therefore, I can get absolutely 0 error if I fit a 20th order polynomial through this. So at this point, you might say, okay, we're done. Go home, we're done. Just fit a 20th order polynomial and you've got the best function. And we'll soon see that this is not the case and why.
Hello.
Yeah.
But that's not possible practically, right? Like that would be overfit, like
going
before the
hello.
Yes,
you're giving the answer away very early. So wait. Yeah, people who've taken the foundations program are not allowed to give answers to some of these questions.
Yeah, got it actually.
Yeah,
I knew that.
Okay. All right.
Rahul, I have a doubt.
Yeah, go ahead.
Yeah, so you mentioned that the sample that we select actually has a significant impact on the estimating function.
Mm-hmm.
So supposing the data is really noisy and then we select a sample which is not really representative of the entire data set, would that like impact these estimations significantly? And
yes, it will. And if you'll wait for like 3-4 minutes, you'll see it.
All right. Okay.
Yeah.
Thank you so much.
Absolutely. But you're absolutely right.
Okay.
You're absolutely and fabulously right. That's totally correct. Okay, so more about approximation, or as I like to call it, learning without noise. So our target, the sign with no noise. We're going to construct a sample from this population. How are we going to do it? We're going to just randomly choose. So if I want to make a sample of 20 points, I randomly choose 20 points like I did here. Okay, that's our game. Okay, now here is what we're trying to do. And this goes to Sukriti, right?
Yeah, Rahul.
Yeah, this goes to your question, right?
Yeah.
In life, you only got a sample, and you want to predict. You don't want to predict on the sample. If all you have to do is to predict on the sample, then put that 20th order polynomial and go home. There's nothing to be done. What you want to do is you want to predict on the population. You don't care about those 1,000 people, whether they'll vote for Trump or whether they'll not vote for Trump. You want to know if the rest of the US is going to vote for Trump or not vote for Trump. At that point, you might want to nuke the US after it votes for Trump again, but that's a different matter. So you want to predict on the entire population. Now, as a result, you want your fits to be robust. And this goes to Sukriti's point, that if your fits changed very much from sample to sample, how could you be sure that the results you got on one sample were generalizable? So there's no robustness, you're out of luck. And this theme of robustness of your fits will come back again and again and again. But informally, you can see that one condition for this is that your sample is actually representative of the population. And one way to think about representativeness is to go back, to this orange points over here and see, do they cover the entire range of my x's well? And you might say, yeah, there's some stuff left out below minus 0.8 and above 0.8. But it actually has points everywhere. So, I wouldn't expect it to do a terribly bad job. But this is 20 samples, right? Out of 100. This is 20 points out of 100. There is the possibility that you might get 20 points chosen out of 100. Generally, 20 points out of 100 has a very high probability of being fairly equally spaced. But it's absolutely likely that 20 points out of 100, the 20 points may be all next to each other and on the left of the graph. And then you would be out of luck, as Sukriti pointed out, on the right side of the graph. So you want your sample to be representative of the population, otherwise you're out of luck. So for that reason, you want a sort of large sample. But let's see what happens if you don't have a large sample. Okay, so on this left side graph over here, I took this and I said, I'm going to make samples of 5 points. So I created 200 samples of 5 points. And for each one of them, I fit a line to these 5 points. And these are the 200 lines I got. Okay, so what's your observation about the left side graph?
More precise.
More concentrated.
There is a concentration, right?
Yeah, there's a concentration. It's more precise.
Yeah, it's more precise. Even though I've only used straight lines, the straight lines seem to want to line up with each other. Can somebody explain to me why?
I think it's because the size is greater than relative to the one on the right.
Yeah, but I mean, yeah. So I mean, it looks like a sample size of 5 seems to be enough to get some good coverage on the sine curve, right?
Yeah.
Yeah. Now look what happens on the right. I've taken samples, 200 samples of only 2 points. Now, if I have 2 points, it's trivial to fit a line, right? You just join the 2 points. But what are the odds of getting 2 points on just the bottom left of the sine curve?
It cannot explain the pattern of the data, probably the curve. It won't be able to explain that if you just have 2 data points.
Yeah, with 2 data points, it does a much worse job, right? You can see it's hairy all over the place. It's like you didn't comb your hair, right? Or if you have my hair and it's uncombable, it's like that. After 6 months of not cutting it. So it's a very kind of hairy graph out there because you're absolutely right. If I get 2 points on the left, right, I get 1 point over here, and you guys can follow my mouse, right?
Yes.
Yeah.
Okay.
Yeah.
So you get 1 point over here and you get 1 point over here. And then you have all this kind of like, you will fit a line like that. And you can see some lines have been fit like that. And the same thing's happening over here. There is more of the distance of the sine curve over here. So it's still more likely you'll get 2 points over here. So you still get some concentration over here. But the concentration is definitely 5 less much less than in the 5 case.
But is it like correct to say, like in case of a, let's say bias sampling also, if we are taking less number of sample points compared to one bias sampling where the sample points are more, so is it correct to say that in case of such sampling where it is biased but sample points are more, overall the curve will be better, like we can get a better predicting system kind of thing?
So that's a complicated question, and let me kind of answer it later. It depends on exactly how that bias happened in your sampling. But that's it's a deep and it's a complex question, and it won't help everybody else right now. So let's take it offline and do it after the class. Yeah.
Yes, sir.
But it's a good question. There's one more question that I want to ask you guys about this. Given that I have only 2 data points over here, should I have fit a line to them?
Not really.
What would have been a better fit if given that I had only 2 data points?
A straight line maybe.
A flat line, right?
Yeah.
Yeah, because it's only 2 data points. Just average the y's out there and give that as your answer. So I think one thing you should realize from this graph is that if you're ever doing any kind of fits, it doesn't depend on how complicated your target is. The target out here is a complicated sine curve. It depends on how much data you have. The complexity of the model you can choose depends on the amount of data you have. So here, because I had 5 points, I can do straight lines. I'm okay. But here, because I had 2 points, straight lines just look very ugly. If I had just done a flat thing over here, then I would have got a much closer band in the center between the between the 2 peaks of the sine curve. Okay, so that's a good thing to think about. So I'm happy that you guys are answering these questions correctly, because that means that you have built up a kind of good intuition about this subject, and you have some natural ability with it. So that's good. Okay, so now let's do another example over here. Actually, you know what? This may be a good point for like a 2-3 minute break. So if you have any questions, please ask.
I haven't got any.
You go ahead.
No, I haven't got any questions.
Okay, anybody with any questions? If nobody pipes up, I'll go on.
Yeah, I have a question.
Yeah.
So we spoke about the degree, right? Like power 5 raised to power 20. So how do we decide what number do we stop at?
Aha. That's the story for the very last slide if you get there. But I'll get there.
Okay, thank you.
Yeah. Okay, so let me do another example. So consider a very simple scenario in which the probability of voting for Romney, so this is from the 2012 elections in the US, is a function of how religious the population in a county is. Okay, so this is the fraction of religious people. X over here, between 0 and 1 is the fraction of religious people. And this is the fraction of the number of people who said they would vote for Romney or who would vote Republican, but specifically Romney in this case. This is completely cooked up data, by the way. But I'm just sort of like saying, trying to motivate this problem. YI is the data that pollsters have taken when they tell us their estimate of the fraction of people voting for Romney, and XI is the fraction of religious people in county I. Okay, so let's assume we have a population of 200 counties, and notice one thing about this population of 200 counties. There seems to be a somewhat higher sampling between 0.6 and 0.8. So this is not uniformly sampled, right? There's like more counties between 60% religiousness and 80% religiousness. Probably fairly representative of the US. So that's the setup of the data set. And we're going to take a sample from this data set. The data set right now is colored in red, and the sample is taken in these blue squares. And you can see these samples. This is actually a reasonable sample of 30 points. It's also a little bit more crowded between 0.6 and 0.8 over here. Okay, so now pretend these red dots are taken away. So we're not told anything about the population, right? We're not told anything about this generating function. I haven't told you how I generated this curve. It's some curve. And I'm not going to tell you how I generated it. You don't know about it. And you're only left with the blue squares. The red stuff is gone. And now your job is to look at these different hypotheses belonging to these different hypothesis sets. Straight lines, cubics, quartics, quintics, 20th order polynomials, 30th order polynomials, 100th order polynomials, and see which one of these does the best job, right? That's your task. Everybody okay with the setup of this problem? Any questions?
No.
No. Okay. So usual, right? We'll first try the straight lines. So I fit a straight line. I find the best fit straight line. It turns out to be this orange curve. Do you think this orange curve could ever look like the data, even if I gave you 1,000,000 points of data?
No, sir.
No.
No, right? It can never get the curve, right? It's a straight line. So this is called bias or misspecification error. Okay, so keep that in mind. That happens when you've used something which does not have enough flexibility to capture the data. Okay, so we first try a straight line, doesn't work really well. Okay, now we try a 20th order polynomial. As somebody pointed out, it has a lot of parameters to wiggle, and because it has a lot of parameters to wiggle, it can fit this data really well. And this is the best fit amongst 20th order polynomials, right? So this is the game we are playing. We're taking every such hypothesis set. Here we took the hypothesis set of straight lines and said, what's the best fit straight line? And that was the orange line there. Here we take all 20th order polynomials, not 19th order, not 18th order, not 17th order, the way we've organized this, but just 20th order polynomials. And said, okay, do a fit. And does it seem to do better? It does, right? So, sample of 30 points of data. Now I'm not showing you the population at all. Which fit is better, the line in the hypothesis set H1 or the curve in the hypothesis set H20?
Curve in the hypothesis H20.
The curve in H20, right? Yeah, super. I'll plot the squared error, and it basically, here's what I didn't plot the square error here by adding it up over all the points, but I just plotted it at each and every point in the population, right? And I said, what does that look like? And you can see what it looks like, by order of magnitude, like literally, the error for the blue curve, or the blue error over here, which is the H1 error, is, or the error when you use G1 to do the fit, is of the order of 10 to the minus 2 to 10 to the minus 6, and this is 10 to the minus 14 to 10 to the minus 30. So the 20th order polynomial is doing much better. I would like to sort of emphasize what I'm kind of doing over here a little bit, because it may help understand. What I'm doing over here is I'm saying that I am looking at all straight lines, and all straight lines, so all functions of the type h1 of x, and the best fit straight line I'm going to call g1 of x. Okay? And then I'm going to look at all 20th order polynomials, i.e. all functions, sorry, not g20, h20 of x. And I'm going to find the best fit out of those, and that's what I'm going to call g20 of x. So that's my notation throughout. In general, I'm going to call hypothesis function h. The best fit hypothesis function is going to become g, and then f of x is the function that actually generated the data. Okay? Are you done with the notation?
Can you again tell us what do we interpret from this plot of squared error?
So from this plot of square error, you're seeing that the 20th or the best fit 20th order polynomial, g20 of x, right? The best fit one. Remember what I'm doing to get this fit. I'm taking all 20th order polynomials and asking which 20th order polynomial minimizes the squared error. You with me on that?
Yes.
Yeah? Okay, so it turns out that, and I showed it to you on the previous graph, there is a particular, I need to get rid of my annotation toolbar to be able to do this. Right, it turns out that there is a particular 20th order polynomial which does that. Let's call that g20 of x. Okay?
Okay.
This is the error that g20 of x has with respect to the data.
Yes.
Except that what I've done is because I have the population, I've taken the data on the entire population to show you this. Yeah?
Right.
Okay. If I didn't have the population, which is the case in the real world, right? I would not be able to show you this graph. Make sense?
Yes. Good.
Yeah. Okay. The annotate toolbar out, clear all annotations. Okay. Let's kill the annotation toolbar. Super. So one of the questions is, how do we generalize from these samples over here to the population? As I told you, I could not show you this graph. And I've shown you the situation where I have the 20th order polynomial doing a much better job than the straight line. How do I generalize from sample to population? This goes back to the question is, how do we make good predictions, right? We want to predict on the population at large. But the conundrum is this. We have not seen the population. If I had seen the population, I would say, well, minimize the risk on the population, minimize the error on the population, right? That's really what I want to do, but I can't do it because I've never seen those points. So what's our strategy out here, right? So strategy is that is something we've already done over here, right? We've minimized the risk on the set of points we have, our sample. And using the sample, we found our G functions. And once we found our G functions, we're starting to hope. We're saying, okay, once we have found our best fit model G, let's just hope our risk does not change out of sample or when using a different set of points. Now, as engineers and scientists, is hope good enough?
Never.
No, right? It's never good enough. We need to actually show this. We need to figure out how to do this. So that's what's going to be the second half of this talk on how we figure out how to do this. The one parenthetical remark I want to add out here is that if your sample was just somewhat representative of the population at least, right? If it was large enough and therefore had a greater chance of being representative of the population, our hope in B is more well-founded. And if it's not, like it wasn't in the sine curves I showed you over here, then it's not very well-founded. Okay. And that's the question of how representative is our sample, right? Okay. So then this is the statement of our learning problem. This is what we want things to happen. We want to find the error, the function G. Yeah, go ahead.
Before we proceed. I mean, why are we even bucketing them separately, like H1 hypothesis being the linear ones and H20s being the separate degree? And can't we even include that degree in the parameters that we are optimizing over? Like,
yeah, you could. How you organize it does depend on, yeah, you could absolutely do that. Why are we organizing it in this fashion? If you try and take too large a set, you will overfit just by having a lot of functions in it. What will end up happening is randomly, so this is somewhat of a subtle and complex point, but you'll just by having terribly huge numbers of possible functions, randomly one of them will fit. And then once you look at it on the population, it won't do such a good job. So it's an overfitting problem. We can talk about it a little bit more later because it's a really subtle overfitting problem. Yeah?
Rahul, so what you're trying to say, Rahul, so what are you trying to say here is, with regards to this question, that if we try to fit a model on the sample, it may or may not necessarily be that it'll fit on the population that perfectly, right?
Yes, and that's the problem we need to deal with, and we'll see examples of this problem very soon. Yeah.
Okay, thank you.
Yeah, but I wanted to make the statement of this kind of learning problem, right? How we are learning models. I want to make the statement of that learning problem. And the statement is part A, this we know, that on our sample, find the G which minimizes, right? Inside a hypothesis set H, find the G which minimizes things for us. Then once you've done that, hope, that's part B, that the out of sample or population error, which I'm calling as R sub out over here, is roughly the same as the small one we found on our sample. So if the sample is representative of this population, this has a chance of being true, but we need to ensure this, right? And that's what we're going to do in the next part. Okay. So one thing I did is I said, okay, I made this prediction on our, using our sample points. Let's see how well the prediction does on the entire population. And in this case, it actually does a bang up good job, as you can see. Kind of makes sense, right? Because it's actually producing the curve back very nicely for us. So it's doing a very good job on the rest of the population. Okay. Okay, so that's a good place to stop and ask some questions of you guys. So normally if we were doing this in a class, there would be kind of exercises, but since I didn't have any of you log on to the site before. We didn't put up exercises on the site. So this would be a good sort of like point to, to talk to ask a few questions. So my first question to you over here, and just, basically just shout out the answer, unmute yourself, shout out the answer, mute yourself back, right? So my first question to you at this point is, how do we find the best fit function on our sample?
By minimizing the errors.
By minimizing the error. Okay. How does the likelihood that we will get a best fit function change with the size of the sample?
The greater the sample, the greater the size of the sample, the greater our accuracy.
Exactly.
Fitting function.
Exactly. What's the problem with extremely low sample sizes, as we saw in the sine curve?
It may not be representative of the population.
It may not be representative of the population. Thank you. So, okay. So I think you've got the three salient points out of this, okay? So what we did so far is we've talked about the theory of approximation, right? There's no noise in this scenario, right? We just have a curve and we're trying to capture it by another curve. We have a curve. Somebody gave us the curve. God gave us this curve. Then God hit us on the head with a hammer and said, okay, go to sleep. 20 years later, we woke up and we said, I don't know what this curve is, and I'll try all kinds of things. I'll try lines, I'll try 20th order polynomials, and try and see what does a good job. And in this case, we found the 20th order polynomial does a good job. So the real world has noise and finite samples. Usually both of these together, mixed up. So you're in a bit of a pickle because you got to deal with all these problems. So here's, a little toy example. Here's what this looks like. Here's my generating function f. Here's my in-sample y. So it's my observed y. These are the samples we saw earlier. We didn't see that actually. We saw the population there. Oh, no. I'm getting a little bit confused. Sorry, my bad. What I've done out here is I've added a bit of noise. The blue squares out here are the sample, but the samples we had earlier, but with some noise added. And the orange dots over here, the orange circles or dots over here, are the population with some noise added. So it doesn't look as clean as this, right? Because now it's all over the place. The red things are the orange things, and the blue things that remain the blue things. But they sit all over the place. Okay. Setup of the problem clear? We now have noise. We still have a sample, we still have a population, and we're going to try and predict from our sample. So far, so good?
Yeah.
Okay. Yes. Where does the noise come from? From many places. So here's an example. Suppose I had 2 counties, and each one of them had 80% of self-identified religious people. Now, on historical trends in the US, if the first county, if 2 such counties, both around 80%, if the first county was made of mostly white people, you'd find that the fraction of those claiming that they would vote for Romney is much larger than in the second one, if the second one is mostly black people. So in that case, race is a much more important predictor. But if you're not predicting versus race, you wouldn't know this. And so you would get some very noisy Y's next to each other. So one may be very high and one may be very low. So you'd get a situation like this, where one was over here and the other one was, the next one was right down there. Okay? So that's what noise does for you. So in other words, we now have a noisy target Y, which is our generating function f of x, which we don't know. Nobody told us. God hit us hit us with a hammer and said, haha, I'm not telling you the generating function. But that's what we got. And we want to approximate it using some function g, which is taken from some hypothesis set, maybe H1, maybe H20, maybe something else. So far, so good? You get what we're trying to do?
Yeah.
Yeah. Okay. All right. Here's my fit using H1. Okay. So I do it on the I do it on the sample, and it's the one with the big blue squares, and it's plotted against the dashed blue line, which is what happens when there was no noise. Now, do you see much of a change?
No.
It's still bad, right? It can't capture the curviness.
Yeah.
So you're like, okay, I'm going to go to my 20th order polynomial to try and do this. Okay, so you go to your 20th order polynomial to try and do this. Okay.
Overfitting.
Yes, but then you may not use the word yet. Anyone who uses the word overfitting must wash their mouth with water. Now, that's what my third standard teacher had told me back in school, because I had said a bad word in class. Well, overfitting is not a bad word here, but still, no overfitting until I write it, right? Don't say that. So what's happening out
Or
here?
we can say over.
You can say it to yourself. So what's happening here? Can somebody explain why this blue curve is going all over the place?
It's trying to capture each and every point in that.
It's trying to capture each and every point. It's got these 20 coefficients or 21 coefficients of wiggle room. So it's trying to go through this point over here. It's trying to go through this point over here. It's trying to go through this point here. And it's trying to go through this point here. And the only way it finds out of going to this point is to go really, really, really high and then come back down. And then get that point and then go really, really down and come back high and get that point. Where does it do a much better job?
In the center of the curve where we have more data.
Exactly, in the center of the curve where we have more data, right? So it does a much better job in the center of the curve where we have much more data. So that's definitely the case. Okay. Now look at this versus the population, and you see how bad it is versus the population. Over here, at least it tried to get all these points over here. It tried to get these blue squares over here. But can you see how bad it does, especially over here, for example, with the orange points? No good, right?
Yeah.
Yeah. So this exactly is overfitting. This best fit G20 has overfit to the sample. Okay. This overfitting is just a fancy word for it's actually fitting to the exact points in your sample. And if your sample is even mildly weird, then you're in, or not representative, you're in trouble. But even if your sample is representative, if you construct a model which has so much wiggle worm space, 20 parameters to wiggle all over the place, you will try and fit to those exact points. And you might get into trouble on the other points. So the takeaway lesson from this is that we must ensure that our model does not fit the noise. And in fact, now H1 is a much better hypothesis space. If I do the same graph I did earlier, the blue one is G1, and the orange is G20. The new G1s and G20, the new best fit line and the new best fit 20th order polynomial. And notice what happens. There is a place that the polynomial does a little bit better, and that's in the middle. And in fact, there are all these undulations where the polynomial goes down very fast. Can you guess what's happening at those points where the error becomes extremely low?
I think that's where there's a lot of concentration of data.
That's where there's a lot of concentration of data, or that's where you have your sample points and that kind of stuff, right? But you go even a little bit away from here, boom, and it becomes comparable to the blue curve, and boom, and it becomes worse. Okay? So how do we systematically decide what is underfit and what is overfit? How do we find a hypothesis set then of the correct complexity? This is the problem that we want to solve, right? So the plot provides us a hint over here. What is the hint that the plot provides us? We just said it. You just said it. At points where there is a lot of concentration, the error is low. But at points where there are not so, but at other points like this one here, where you don't have the samples. I have, by the way, put all the samples we had in all the points in our sample. I've shown with these pinkish reddish lines going down. So there are no points near the sample. What's happening? Can somebody tell me?
There's high error, I guess.
The error is high. So if I can somehow fit at points not on the sample, not in the sample, I would be able to diagnose this problem by looking at the high error. Does that make sense?
Can you repeat? I didn't quite catch that, sir.
So if I was somehow or the other able to get some other points which were not inside my sample, like a point like this, where my mouse is,
yeah,
I would be able to diagnose this problem with G20 because the error would be extremely high. Does that make sense?
Yeah.
Okay. So, am I not stuck though? All I have is my sample. I don't have the population. So can anybody come up with a strategy to fix this?
At the extremities, like you are working on the most extreme points. So you just have to look at them, because in the dense part of the data, both the curves are performing approximately the same. So why do you need more points where we are missing them?
Because you want to make a prediction all over the function, right? All over the range of the function, not just at the points where you have data, right?
Reduce the degree.
Yes, sir. Can we reduce the degree? Maybe like, because we can see if it is G1, we are getting a kind of graph, and G20 we are getting a different one. So maybe somewhere like.
No, somewhere in between. No, I totally get where you're going with that, and I think that's actually a really good idea. But so 2 points over here. I think Maitri is this. Did I get your name right?
Yes, it's Maitri.
So she's making the point that why on earth are we trying to predict out here? There are no samples out here. So there are 2 reasons to do that. One is that you don't know that any other sample may not have had samples here. If it was like way to the left and way to the right, so you might say, okay, that's not within our range of prediction. I don't care about it. I'm not going to predict over that. In fact, you might say if you only care for counties between 55% and 85%, this is good enough. You could even take the 20th order polynomial, go home, and you'd be right to make that statement. But you can even see these undulations over here, right? So if you look at this one where my mouse is, extremely low error here, and the error suddenly popped up. So it's like I take an infinitesimal step over to the right and my error suddenly pops up a huge amount. It's not behaving in a very robust fashion. Does that make sense?
Yeah, it does.
Yeah, it's not being very robust. So that's kind of like a bad thing. When you have, when you're trying to predict things and things are not robust, then you should really be worried about your predictions over there. So the question I'm asking you though is, based on this notion that if I go even a little bit away, the error becomes that high, how might I construct, and given the fact that you don't have a population, how might you construct a mechanism to use this large error to diagnose that this 20th order polynomial is a bad model?
So Rahul, I think one of the ways could be to just take multiple buckets of these samples, like randomly selected buckets, and then iteratively see if across all those smaller buckets, what the error is like.
What the error is like. So what you're saying is basically
carve
out a smaller bucket.
Yeah.
Yeah. So that's exactly it. That's exactly the idea. And what Sukriti described was actually the even more complex form of it, which is called cross-validation. But this is exactly the idea of what she said is you take your sample, you split your sample into a training set and a randomly chosen validation set or test set. So instead of adding, because we have no capability to add because we have no due data, we subtract. We say take something away from this data and keep a little bit of that data out and then see what the error is on that. And Sukriti's, I think, very good idea was actually taking buckets all over the place and look at those buckets, because that'll give you an even more robust answer. Okay, so absolutely. So that's the way to do this. Now I want you to, so one more question. So I'm sorry I'm peppering you with so much questions, but it's kind of fun to go in a question answer sort of fashion. Now it must have dawned upon you that you're taking your already small sample and making it smaller by doing this.
Yeah.
Based on your knowledge now from seeing that sine curve example with 5 data points and 2 data points, what kind of a model will this force you towards?
A not so generalized one.
Pardon me?
Not so generalized one.
Is it a not so generalized one, or is it a, think about what we did there, right? We used a straight line for the 5 data points and we used a straight line for the 2 data points. Which one was worse?
The 2 one.
The 2
it
one,
would
right?
not explain the data set that that well.
Okay, so it may not be able to capture the entire data set that well. So is it a more complex model or a less complex model you're being forced towards?
Less complex.
Less complex model, right? Exactly. And that in this situation may be a good thing because you see that G20 seems to be too complex. It's doing these undulations. It's going up and down. It's going all over the place. Yeah? Did that point become clear?
Yeah.
Okay. Okay. So just for fun, I'm going to do that sine curve thing again. So I'm going to take 200 samples of size 30 from the population and fit a straight line and a 20th order polynomial to each one of these. And I'll plot them all in one plot. And even before you see it, I want you to guess what the plot's going to look like. So first, let's talk about the straight lines. I'm taking 200 samples of size 30 from our population, and I'm going to show you all the straight lines. Are they going to be all over the place?
They're going to be all over the place and not.
Or are they going to be more or less pointing in the same direction?
They'll be all over the place for a straight line and not concentrated around the straight line.
How about for the 20th order polynomial?
It could be concentrated around the the line that the 20th order polynomial creates.
But the 20th order polynomial, remember, is not a line, it's a curve.
Sorry, the curve.
Okay, let's see if this is the case. So I think you got it exactly the opposite. But can somebody explain what's happening on the left?
It's not generalizing the whole population so well.
No, it's not a question of not generalizing. So which do you think is a better generalizer, the one on the left or the one on the right?
Comparatively, the one on the left.
The one on the left, right? So it's actually generalizing it much better. It's not generalizing in the sense that it does not get you the curviness, right? But remember, you never see the red curve. You only see the orange points and the blue points. So the population is the orange points. I would argue that all of those curves are actually doing a good job of going in between the orange points. They're not doing a terribly good job, but it's giving you the rough idea of going from the bottom left to the upper right, correct?
Yeah, correct.
So in that sense, all the predictions, all those 200 models are much more robust. But having said that, I will never capture the curviness of the red curve, right? So that's my bias. So that's my bias limit. I mean the bias side of things by doing that. Okay. What happened on the right? This looks like a really, really, really bad hair day, doesn't it?
It's a very sensitive model. Right?
It's very sensitive. Every time I change my points a little bit, it goes off in some other place. And that's why I get all this hair over here and I get all this hair over here. And only over here, when I have lots and lots of sample points, lots and lots of blue points over here, and lots of population points, lots of orange points, therefore, every sample I create is likely to get more points from here, that I get a much more tighter fit out here. But wherever I have less possibility of getting samples, I do much worse. So in other words, I'm taking this and repeating it again and again and again with different samples, different randomly chosen samples, and getting different curves over here. So this sort of illustrates to you how bad this 20th order polynomial is. Yeah? Yeah, there was a question. Go ahead.
Is it also because, so can we say that the sample is not really a good representation of the population because it is so widely spread out over the curve?
So that's a very dangerous statement to make, and I'll tell you why it's a dangerous statement to make. You are choosing 30 points out of 200. Likelihood is that, with choosing as many as 30 points out of 200, you'll get a good spread all over the curve, right, of these points. You're absolutely right. There'll be some of them for which you don't. And then that's coming because your sample is not represented. But there is a second part of it, which is at play over here. So the first problem, which you very nicely stated, is that the sample may not be representative. But the second problem is that you've tried to fit a model that is so complicated that it's actually fitting to the noise on any one of these samples rather than the signal. And because it's fitting to the noise, it's giving you these highly undulating curves. It's giving you multiple such curves, right? Multiple such curves. And when you look at these multiple such curves, you have no predictability left. Because on one curve, it might be over here, and the other curve, it might be there, and the third curve, it might be down there, and all kinds of stuff. In fact, perhaps a nicer way to see it is in this graph over here. So here's what I did is I took all the coefficients in my 20th order polynomial, and all my coefficients in my line. That is my second order polynomial, my best fits. Okay, all 200 of those because I did these 200 samples. And look at the, I can't even show you as compared to the other polynomials, all the possible values I get. But just look at, for example, coefficient 2, which is the coefficient of the quadratic. It ranges all the way from 10 to the minus 10 to the 10 to plus 10 to the 10. 10 to the 10, right? That's roughly like 10 to the 3 to the 3. So that's roughly speaking a billion. It's going from a billion to a minus billion. Do you expect to have a stable polynomial with such high coefficient values?
Not at all. Not really.
Not at all, right? So that's exactly what's happening here, that each time I just change the sample slightly and boom, I get a completely different fit. Not predictable at all, not robust at all, bad, right? Okay. So let me come to the last part then, in the last 5 minutes or so, or 5-6 minutes that we have over here, and talk about how are we going to do it. And you guys just told me how to do it. Keep a held out set. Take some part of the sample and leave it out. Okay, so I don't have to say much about this because you told me what to do. High sensitivity to samples is a very bad sign. You can get larger samples so that they're more representative. You can fit simpler models, and really, typically, it's a combination of those two things you're doing. And remember that the complexity of the model you fit depends upon the size of the data set you have. So if you're going to take some data away by keeping a holdout set, you'll naturally be forced to a more simple model. So that was that example again, right, of the sine curves. Okay. So now this comes up to the final part of our talk, right? This idea of model comparison. We've been postponing this to the end because we didn't have a strategy to do it, but now we do. I forget who, but somebody said over here, why don't we choose something which is not as low as 1 and not as high as 20? And you're absolutely right. Because 20 is too complex, 1 is too simple. It's going to be something in between. But how are we going to fit it, right? Well, let's go back to our ideas, right? The error must be smallest on our sample. And we've talked about interpolation, right? Where we actually just, use 20 points and use a 20th order polynomial. And then you'll get exact fit, you'll get completely zero error, and you can't do anything. And then we talked about the fix, which is to leave a little bit of the thing out and check the error on that little bit of thing you left out, which we'll call a held out set or a validation set or a test set. Okay. So that takes us to the part B, right? Where we want our out of sample error to be roughly the same as our in sample error. But now, with this idea of taking the small little set out, if that small little set can be a proxy for the population, right? Then I can actually calculate the error on that and say, well, that error is very similar to the error on the sample or whatever is left of the sample, and then I'm good. So do you get the idea over here? The first part is, well, take the part of your sample which you're going to train on. We're going to call it the training set. Train on that set, get the best fit, and then look at the error. That's A. B is whatever you left out, which you're going to call the held out set, the validation set, or the test set. Calculate the error on that and check if it is roughly the same as this or not. If it is much higher, is that a good hypothesis? Hello? Anybody?
That will be overfitting, I guess.
Yeah, it would be overfitting. The error is much larger, which means that, any attempt at generalization has gone bad because my error has become extremely large. My polynomial has gone off somewhere towards infinity, right? Yes, the model should not be too complex, or a small perturbation in coverage going from the sample to population will sink us. Okay, so let's do this. So this is how we're going to do it. Here's the schematic for what you've been saying. We're going to hold out some data called the test set or validation set. Leave the training data out. So here's what I did for my 30 points. I have 1, 2, 3, 4, 5, 6 green points which are left out, and I have 24 points now. So instead of fitting on 30 points, I'm going to fit on 24 points. Find the best fit model, calculate the error of that best fit model on the 1, 2, 3, 4, 5, 6 points. sum the squares of the errors, and divide by 6. This is what I'm saying making sense?
Yeah.
Yeah? Okay. Then what am I going to do? I'm going to do this for each and every hypothesis set, right? I'm going to take lines, quadratics, quintics, hextics, seventics, whatever I don't know what you call a 7th order polynomial. And then I'm going to tell you on these 6 points, what's that error for each and every one of these degrees of polynomials. Make sense?
Yeah.
And I hope you're getting this kind of notion out here that the degree of polynomials sort of is a proxy for the complexity of the model, right? With the higher the degree of the polynomial, the more complex it being. Okay. So the held out, so now the next part is what we were saying, is that the held out set is going to be a proxy for the population. One can show that this is actually good. This is actually true. One can show that the error on the held out set estimates the population error. But it turns out that this proof is actually not that easy, but it's doable. But it's not surprising because the held out set is just another sample. And hopefully it has the variability that the other samples have.
Rahul, can I ask
Yeah.
a question?
Question? Yeah, go ahead.
So for example, if we are testing out different, different functions probably, so one of them might fit the, the held out set that we are testing upon, and the other one might not. But if we compare, just in the real world scenario, if you look at the population, what if, let's say the 20th order polynomial fits the population much better than the first order polynomial?
So is it possible that a 20th order polynomial will fit the population better? Yes, it is. It though is unlikely if your sample is large enough. And if you did what Sukriti said, which is to take multiple buckets of multiple samples and average over the sample, something called cross-validation, it's very unlikely to happen, right? Because you've chosen these multiple buckets all over the place. With any one bucket, you're absolutely right.
Okay.
Yeah. So if you want to learn more about all this, AI1, which Pavlos is going to do in a few days now, well, a few days being something of the order of like a month, on September 15th, actually goes into this in a huge amount of detail. It does a lot of stuff on validation, cross-validation, all of these kind of things. In this kind of introductory lecture, I really don't have the time to do it. Otherwise, I could have. But so there's this idea of validation, but you're absolutely right. If you wanted even that to be robust, average it over multiple validation sets.
Yes, that is what I was thinking.
Yeah.
Yeah.
Absolutely. Thank you. Very good point. Okay. So we're using now this held out set to be a proxy of the population, though we should actually average it over multiple held out sets. Thank you for bringing up that point. Okay. So now we're going to evaluate the error on held out set. So let me just repeat the process so it becomes blindingly clear what we're doing. For every polynomial degree D, we are minimizing the training risk. So on the sample, which is what is left over after taking out the held out set. So we are fitting a model for each hypothesis space, H1, H2, H20, H21, and we are finding the coefficients which give us the best fit model, right? Then we are evaluating the error on the held out or validation set. At some point, you'll see that what's happening is because your polynomials are going up and down and up and down and up and down and behaving completely crazy, you're going to see that this validation set risk on this held out set starts going up. This error starts going up. And you see that happening around maybe about a degree of 11 or 12, and it just starts going up. By the way, in case you want to see how bad this is, the Y scale is a log scale here. So like over here at like this, it's like 100 times worse than it is, well, not even 100, 10,000 times worse than it's over here. Just so you know, this is on the log scale, this is not on the linear scale at all. Okay. So what we're doing now is we're looking at this side. So should I choose any model where this is going up?
We can't.
We can't, right? These are not robust. So it seems that there is an area of robustness which goes somewhere between a degree of 11 and a degree of 1. And maybe it's kind of actually even better over here. Sort of between a degree of 6 and a degree of 1. Any one of these models would do a reasonable job. Up to like 6th order polynomials would do a reasonable job of capturing this data without a huge amount. Turns out that the exact minimum is at d is equal to 3, but that's not really the most important thing because these things are so close to each other. So look what's happening, right? We wanted to minimize the error on this blue set. But as I've told you that, by the time you keep going down and down and down further to the higher and higher order polynomials, this is going to go towards 0. Makes sense, right? Because I can always interpolate at some point. So that's not useful. It's not useful to be here just because it's 0. But then we hit upon this idea that we are actually going to calculate this on this held out set or this validation set. And what do we want on that? We want it to be as close as possible to that on the training set. And you can see it is close until it starts diverging. And here is where it starts diverging around 6. And so where it kind of converges very closely is out here. It converges reasonably closely out here too, but that may be a little bit of a red herring. But you could actually, because doing a polynomial of order 0 may not be the best idea. The error is already high. So you want the error low, which is here. And you want the two errors, the orange error and the blue error, to be kind of the same, which is here. So it satisfies our two conditions. And that's it. That's how you evaluate every freaking machine learning model. There's really no more to it. There's more complicated ways of doing it, much more robust ways of doing it, like cross-validation. But this is the basic idea. And this is the famous complexity plot. As the complexity of your model goes up, find the sweet spot, which is given to you by this kind of red line over here, which is the balance between overfitting, where you're having too complex a model, and underfitting, where you're having too low complexity a model, where the training error is low and the test error is also as low. Now you can notice up here, as you go to the left, you could actually make the difference between these two less, which is our second point. But if you did that, then the error would be still a little bit higher, and that's not what you want. You want the error to be as low as possible. Okay, and that's it. So I went over a little bit by about 5-6 minutes. Sorry for that. But that's really all there is to actually evaluating machine learning models. And every machine learning model you do, whether it's a linear regression, logistic regression, deep neural network model, there will be some kind of notion of complexity. And you will try and figure out how to deal with this complexity by finding out the sweet spot. Now, one thing I didn't talk about, and Pavlos will talk a lot about in AI1, is regularization. And regularization is this kind of idea where what you're doing is you're taming these coefficients. You're letting your model be as complex as possible, but you're taming the coefficients to be, to not have those high values, and you do it by imposing some additional penalties. And regularization is used a lot in deep neural networks using techniques such as batch normalization, dropout, and weight decay. But that's, of course, a topic for a totally different day.